The topic for today is radial basis functions. Before going into the network details, we will be talking about the very basics of what radial basis functions mean, and in that we will be covering one of the very important theorems, one of the fundamental theorems upon which this radial basis function is based upon, and that is Covers Theorem. So we will be treating the fundamentals as well as the Covers Theorem in today's lecture. But before we begin this topic, there are one or two discussions that I wanted to have related to the backpropagation algorithm. In fact, we have been seeing about several aspects of the backpropagation algorithm so far, and one of the things which backpropagation algorithm has to take care is the question of generalization. And what we mean by generalization is that if you have trained the multilayered perceptron with backpropagation algorithm with several input-output pair of patterns, okay, I mean it knows that how to train the system for the test patterns, for the training patterns, but whenever you feed a test pattern, okay, then what is the guarantee that the test pattern is correctly, we are obtaining the correct kind of output for the test patterns, okay. We can only have that because the test data was not there during the training. I mean in general it will be so that you will be having a separate set of data set for the training and a separate data for the test. So the test data doesn't necessarily include any training data. If accidentally there is some training data, well and fine, I mean then it will be very correctly classified if the problem is a classification problem. But in general I think we cannot really say that that the test data will be generating the proper output. It does if there is a proper generalization. What I mean to say is something like this, like say for example we have got some input-output function, okay. The function as such is not known to us, I mean known to us in the sense that we are determining the function through the training process, right. So here we have the output, okay, and here we have the input, although I am considering the input set of points in one dimension, but in general it will be in the multidimensional space. So let us say that this is one input, this is one input, this is one input, this is one input, and this is another input, say this is another input, like that. And for these inputs, okay, the corresponding outputs are obtained here, like if this much is the input, okay, then the corresponding output is here. If this is the input, this is the corresponding output. Now the thing is that these are, I mean all the crosses that I have given in this drawing, they are the training patterns. All these are the training patterns where their input-output behavior is known, right. Now what the neural network does is that with the training, okay, it fits a curve, okay. Essentially neural network training is nothing but a curve fitting problem. So we fit a curve like this. If it is a good fit, okay, if it is a good fitting, then we should be expecting a curve like this. Now these are all the training patterns, and supposing we introduce some test patterns, okay, and let us say that one of the inputs to the test pattern is here, okay. Now this point is certainly not there in the training because there is no cross at this point. So we introduce a test pattern here, means we feed the input over here and we see the output. So the output should be this if there is a good generalization. If I have a test pattern here, okay, then given this kind of a functional approximation that the trained neural network is doing, we will be getting this as output. Now the question is that yes, if the curve is like this, okay, then we are getting the, for the test patterns also we are getting the correct kind of outputs. But let us say that taking the same crosses here, I mean we remark the cross positions, that means our training pattern positions, okay, and we have, let us say, realized another function, okay, which is not that well generalized. See, training pattern you feed means that, I mean of course the function that you are approximating, it has to pass through the training pattern points. So, there is no harm in fitting a function like this. Who says that it is bad? Because this function which I have drawn with blue, okay, this is also passing through all the training patterns, okay. But if I have to accept this blue function, okay, as my approximating function, then for this input I would be getting this as the output, not this, and for this input I will be getting this as the output, not this. But question is that when you see an output of this kind or an output of this kind, would you say that it is generalized? It is not, because I mean although we have trained it, but it lacks generalization. Now, many a times the generalization lacking is due to what is called as the overfitting of the data. By overfitting, I would like to say that, okay, you take a training set, okay. Now, a training set, how are you deriving? I mean people derive it using the, I mean from the real life examples, okay. I mean from the actual process or from the actual data that is available, some sample data which are available, they are used for training. Now, such kind of data are always subjected to some noise, okay. There may be some noise that is present in the training pattern itself. Now, if I mean supposing this is the set of patterns, okay, that with which I have trained. Now, supposing I have got one odd point, one outlier, let us say, that supposing in this training patterns that I have got with which I have trained, supposing there is a pattern over here, means this is here and then the next is here. Now, clearly this is an outlier that it does not fit into any proper curve fitting, a proper smooth curve fitting will not fit this point. So, this is definitely a noisy point. But if I make the neural network properly trained with all these training data without bothering that whether it is a noisy data or whether it is the right kind of data, neural network will faithfully train it, and when it trains it will realize a function, okay, where such kind of generalization will be lacking, because it also learns the noisy data. That is the thing. Because it learns noisy data, there will be errors that it will be making when the test patterns are presented. Now, the question is that on what are the factors on which this generalization is influenced, okay. Now, the generalization of the capability of the backpropagation algorithm is influenced by three factors, okay. So, generalization is affected by three factors, and what are they? Number one, very important, is the size of the training set, okay. Now, again I think this aspect we have discussed implicitly many a times, okay. I think even during the discussions of the single layer perceptrons we have talked about this aspect, and in fact you remember that we also talked about the VC dimension, which determines that what is the size of the training set up to which we can go, okay. And then the second factor is the architecture of the network. Now, it may be that your training set is fixed, okay, but you can go through different architectures, like say for example in the backpropagation algorithm only for multi-layer perceptrons, you can design the architecture in a different way. You can have different number of hidden layers, you can choose different hidden layer neurons, okay, different number of hidden layer neurons in a hidden layer, Okay. That is to say that you can influence the architecture of the network. And the third factor, of course, it is not under anybody's control because it is very much problem dependent, that is the physical complexity of the problem at hand. Okay. Now, we do not have, I mean, as I told you that we do not have any control over this thing, that whatever problem we have been given to solve, we have to solve that. So, what we can do is that we can instead study these two effects, that is to say the size of the training set and the architecture of the network. Now, we cannot simultaneously vary the both. So, we can see that by keeping an architecture of the network fixed, okay, if we try to experiment upon the size of the training set, okay, then obviously we should get some result, and it is seen that if you fix up the architecture, okay, and determine the size of the training set, then the size of the training set, that is n, if n is the size of the training set, that will be given by the order of W by epsilon, where W is the number of free parameters in the network. So, W is the number of free parameters and epsilon is the fraction of permitted classification error, fraction of permissible classification error, okay, which means to say that if supposing epsilon is equal to 0.01, 0.01 means that we can tolerate 1% of classification error, okay, and then W could be anything. So, if it is W by epsilon and if epsilon is equal to 0.01, that means to say that it is order of 100 times W. So, whatever number of free parameters are, okay, it should be 100 times of that. That should be the training, I mean the size of the training set, okay. So, naturally if you are wanting the fraction of permissible classification error to be very low, then you have to go in for a very large training set for a good generalization, okay. And the other thing that one can study is that you keep the size of the training set fixed and then you find out the architecture, okay. Now, lot of such studies have been made and I am not going into the details of it because we have already covered several lectures related to the backpropagation network, and in fact, I expect that those who are attending this course, okay, they should I mean also have their own study. I mean they should I mean I should also encourage them to have some self study with the materials that are available in various books and journals, okay, just to study more about the aspects of the multilayered perceptron, so that when it comes to the solution of your problems, you can help it. I mean you can try to use it for your benefit, okay. So, having said that, I think we can afford to move over to the next topic that we are going to cover, and that, as I told you, is the radial basis function. And in this we are first going to cover a very basic theorem that is presented by Cover, okay. Now, before we go into the Covers theorem, I think it is better that we spend some time, okay, discussing about the very basic fundamentals of the radial basis functions, okay. Now, radial basis function structurally is a multilayer perceptron, okay. But the thing is that whether we are calling, I mean we are certainly not going to call every multilayer perceptron as a radial basis function. Now, you have seen that we have gone through the backpropagation algorithm for the multilayer perceptron, and the backpropagation, if you are looking at the theory behind the backpropagation, after all, what is a backpropagation? You are making a stochastic approximation to the process that you are going to solve, okay. You are I mean essentially by learning through the examples, okay, and adjusting your free parameters, you are basically making a stochastic approximation, and then you are, I mean after the training you are going to use it for the test patterns. So, the whole approach is that, please keep in mind, it is a stochastic approximation approach. Whereas, you can view the same problem of multilayer perceptron from a different angle. You can look at it purely from a surface fitting consideration. Okay. What I mean by surface fitting consideration, let me try to illustrate it a bit. Okay. Now, let us go back to the point where we had talked about the advantage of the multilayer perceptron that we had spoken earlier. The advantage that is there is that if we have a set of patterns, okay, which are not linearly separable, then we could not solve it using single layer perceptron, because the very basics of the single layer perceptron is that you have to determine a hyperplane in the m dimensional space that can clearly separate the patterns, I mean from one that can clearly separate one class of patterns from the other. Now, why is it that we could solve the non-linearly separable problems using the multilayer perceptron? We did it because we had mapped those input functions into a hidden layer, and then we went over to the hidden space. Now, individually, I think you remember the example that I had talked of in one of the earlier classes, where we had shown the example of an exclusive OR. Now, the hidden layer which was there, those hidden layer on its own were making a linear separability of the patterns, but combinedly together in the combined output space, we had got that there was a separability, although with respect to the input space the patterns were not linearly separable, but still we could do because of the in between mapping that we do to the hidden layer. Now, it is the same idea, only thing is that in backpropagation algorithm you are using a stochastic approximation. The debate that you can have is that rather than having that stochastic approximation, why don't you start afresh and try to think it in terms of a surface fitting. Surface fitting like what? That, okay, let the set of patterns that we have at our disposal be not linearly separable. Okay. Let it be non-linearly separable, or we do not know. I mean, when we cannot pass any hyperplane, we are saying that it is not linearly separable, and inevitably we are going to have that kind of situations many a times in practice. Now, the question is that if the pattern is not linearly separable, if you have a space like this, like say for example, it is very difficult to draw a multidimensional space, but let us say that here we have got pattern class 1, okay, somewhere, and let us say that we have another pattern class 2, okay, which are like this, okay, in a multidimensional space. Now, they may not be linearly separable, means I may not be, I mean this is a 3-dimensional plane example, and I may not be able to cut it through a plane that separates the class of this from the class of this. Okay. Okay, I cannot pass a hyperplane, but you never know, I may be, I may be able to pass a hypersphere or any hyperquadric surface, meaning that any multidimensional surface. I mean, I could be having a surface like this that can clearly separate the patterns. So, the thing is that if from the training set, I mean if I am given with a training set that is non-linearly separable, okay, then my problem will be to determine a surface, a hypersurface, not a hyperplane anymore, a hypersurface that can make the classification between the two competing classes. Okay. Again, I mean the Fact that I have taken example of 2 classes does not mean that it cannot be extended. It can indeed be extended to multiple number of classes also. The same idea extends. In fact, we had talked about the extension into the multi-class classification in the last lecture itself. The thing is that then what happens? That then I mean, we are looking at a surface fitting problem in the multidimensional space. So, that is what forms the essence of the radial basis function, that is fitment of the multidimensional surface. Okay. Now, to do that, what we have to do is that just like any multi-layer perceptron, we have to have a hidden layer in between, at least one hidden layer in between. Okay. And what is that hidden layer? And in a surface fitting problem, we can look at the hidden layer from a different perspective. We can say that the hidden units which are there, the hidden layer units which are the neurons which are there, they provide a set of functions which forms a basis for mapping into the hidden layer space. I mean, basically we are going to do a mapping from the input space to the hidden layer space. Okay. And to do that mapping, we need some basis functions, which who is providing? The neurons in the hidden layer, they are providing. So, the hidden neurons providing the basis functions, and this kind of architecture is called as the radial basis function networks. Okay. Now, the basic form of radial basis function is that it has got 3 layers. I mean, I am saying that it is the very basic form of radial basis function. Of course, I mean researches are on for multi layer things also, but of course, I think I mean the problem, the way it is solved, it is I mean nicely done for 3 layers also. So, the basic form, I should say that the basic form of the radial basis function is, in its basic form, it is having 3 layers. And what are the 3 layers? First is of course the input. The input of course contains the source nodes, okay, which are connected to the environment. Then we will be having hidden layer. In fact, since we are having 3 layers altogether, we can have only one hidden layer in the basic form. Okay. Only one layer, okay, which does a nonlinear transformation. This is very important. It does a nonlinear transformation, okay, from what to what? Nonlinear transformation from input space to the hidden space. Okay. And very interestingly, it is found that most of the times we find that the hidden space dimensionality is higher. In fact, that is the I mean that is based on the theory that Covers had proposed, what we are going to discuss shortly. So, the dimensionality of hidden space is definitely higher. Okay. So, hidden space with higher dimensionality, and then we are having the output layer, okay. The output layer that supplies the response. Okay. So, this is the 3 layered structure. Okay. Now, yes, stressing on the nonlinear, and let us see that why should it be a nonlinear. You see, if the input itself is a nonlinearly separable pattern, that is what we are assuming, right, that input is nonlinearly separable. In that case, I mean theoretically it should be possible for us to design a mapping function, a mapping to a higher dimensionality, where in that space, in that higher dimensional space, it will be linearly separable. If we can have that, if we can design a mapping, okay, from non-linearly separable input space to linearly separable hidden space, okay, if in that hidden space a hyperplane separation works, then our job is done. Then we can use that, okay, for the solution of our problem. So, from the non-linear to the linear, if it has to map, then certainly it cannot be a linear function mapping, it has to be a non-linear function mapping. Okay. Now, with that basic form of RBF, we come to the Covers theorem. Okay. So, we first build up the basics of the derivation, although we will not cover the derivation in great details. Okay. Now, before we go into the discussion on Covers theorem, let me tell the statement of Covers theorem. It says that a pattern classification problem cast in high dimensional space is more likely to be linearly separable than in a low dimension space. I repeat, a problem is more likely to be linearly separable in higher dimensional space than it is in lower dimensional space. Okay. So, that is why it makes sense in doing a mapping from the lower dimensional input space to some higher dimensional hidden space. Okay. So, having said that, I think we should write it down because the statement of that is very important. So, this is what it is. So, that is why we should be considering the mapping from the low dimension to the higher dimensional space. Okay. So, that our idea will be to make it linearly separable in the mapped space. What is non-linearly separable in input space should be linearly separable in the mapped space. Now, in order to discuss about that, let us consider a set of patterns. Okay. We define a set H. Okay. We define a set H of n patterns, and what are those n patterns that we are having? Let us denote them as x1, x2 up to xn. Okay. And each of these patterns, each of these n patterns can be assigned. So, each can be assigned to two classes, and what are those two classes? To H1 or H2. So, there are just existence of two classes. Now, this set of patterns, okay, this dichotomy of patterns, because this is binary, so we can call it as a dichotomy of patterns. This is separable with respect to a family of surfaces if there exists a surface in that family that separates H1 from H2. Okay. Now, again, I mean, in order to explain this, let us say that we have got a multidimensional space where we are having patterns of one type, patterns of another type. Okay. And the thing is that if there exists a surface that separates the patterns this from, I mean the surface may be like this, that if a surface exists that separates the two classes of patterns, then we can say that this dichotomy, this set of patterns, this set of binary patterns are separable with respect to that surface. Okay. Or to say that if we have got a family of such surfaces, okay, then if at least in one of the members of that family, okay, it is separable, we can say that it is separable with respect to that family of classes. All right. Now, okay, this can be, I mean the ideas will get more clear as we proceed. Okay. Now, what we do is that for each of the pattern, I mean let us take a pattern X, okay, which belongs to the set H. So, X pattern, X vector belonging to a, for each of this pattern, for each X belonging to H, okay, let us define a vector which is made up of a set of real valued functions. Okay. So, we define a vector made of a set of real valued function. And what are those how are we going to write that set? Okay, that vector will be written as like this, I mean the set of real valued functions. So, we will be defining a real valued function phi I of x vector, okay, given that I is equal to 1, 2 up to some number, let us say m1. So, that means to say what? That we have got m1 number of different functions, m1 number of different real valued functions are available, phi 1, phi 2, phi 3 up to phi m1. There are m1 number of real valued functions which are available with us as a set. And with this set of functions, we can map x into what? We can map x into phi x. Okay. So, given some x, okay, it can be mapped into phi 1 x, phi 2 x, so on up to phi m1 x. So, m1 such different mappings will be possible, okay, if we take a set of such real valued functions. Okay. Now, we take these, I mean we refer to these phi I functions, okay, as the hidden functions. So, all these phi i's, okay, all these set of functions, they are referred to as a hidden function because it plays a role very similar to the hidden units in the multilayer perceptron. Okay. Now that we have got m1 different such real valued functions available, okay, that essentially spans a space. Okay. So, the space that is spanned, so the space that is spanned by the set of hidden functions. So, the set of hidden functions I can write as the set of phi I x, okay, I is equal to 1 to m1. This is referred to as the hidden space or feature space. Okay. So, what was our input space? Our input space is, see, these are input space will be the dimensionality of this x vector. The dimensionality of this x vector we have been taking as m, all the time we are taking it as m. Okay. Since it is essentially pertaining to the input, we can call it as m0. So, let us say that the dimensionality of x is m0. So, we are mapping this x into a new space, okay, whose dimensionality is M1, because there are M1 number of such real valued functions, and I mean what cover is going to show is that M1 should be as high as possible, okay, preferably greater than M0. I mean it does not explicitly say that it has to be greater than M0, but okay, the findings of cover is that M1 should be, I mean higher you choose M1, okay, higher you can map into these, okay, the better it is for the linear separability. Okay. Now, what happens is that, okay, you have got this set of 5 functions, okay, or what you can say as the hidden functions spanning a hidden space of M1 dimension. Now, we can say that a dichotomy H1 and H2, because we have got only 2 classes over here, H1 H2 dichotomy is phi separable. The definition of the phi separability is what? I mean it is just putting the mathematical words into what I had already talked of at the beginning of our discussions on Covers theorem, that this dichotomy is phi separable if there exists an M1 dimensional vector. If there exists one M1 dimensional vector in fact, finding out one such M1 dimensional vector itself is good enough, all right, because if we choose a family of functions, after all we have chosen a family of functions, isn't it? There are M1 number of such functions, and if out of these M1 functions one fulfills the separability criteria, then we can say that okay, using the phi functions is worth it, because at least one member of this phi function is able to solve our problem. Okay. So, if there exists one M1 dimensional vector, and what is the separability condition? That is very simple, our good old separability condition, that in the phi space, okay, in the phi space the separability condition should be that W transpose phi x vector should be greater than 0. I mean if that is the case, then we can say that x belongs to one of the classes, let us say H1. If this is greater than 0, then x belongs to H1, and if W transpose phi x is less than 0, okay, the vector x belongs to the classification to the class H2. That means to say that the hyperplane that we are defining, so the hyperplane equation, that is W transpose phi x vector, which is basically is equal to 0, this being the hyperplane equation, this is the separating surface. A hyperplane is the separating surface in the phi space. So, to find a network like this, so to have this situation fulfilled, what is the condition? That in the phi space the function must be linearly separable, because it is a linear separability condition in the phi space. But phi space is not the one that is your input. Your input is a different space. You are mapping from the input to the phi space. So, now you have found out a good surface in the phi space, a linearly separable surface in the phi space. If you do a reverse mapping of that surface, which is a hyperplane in the phi space, if you reverse map it to the input space, it will no longer remain as a hyperplane. It will remain as a, it will be a hypersurface, a general hypersurface it will be. So, the inverse image of the hyperplane, if you see, okay, that is to say that the inverse image of this hyperplane and this inverse image will be written as x mapped to W transpose phi x equal to 0. So, if we do the inverse mapping of this into the x space, okay, that will define the separating surface in the input space, okay, which is not a hyperplane anymore, it is a hypersurface. It is a general hypersurface. So, now the thing is that, so we are not going to, so that means to say that the separability problem that we are addressing at the moment with respect to, while seeing with respect to the input space, it no longer remains as a linear separability problem, it is essentially a nonlinear separability problem. So, now let us think afresh and try to model a non-linearly separable function. Okay. So, in the input space itself, if we try to model a non-linearly separable function, then we can do it like this. Okay. So, we can express such kind of non-linear separability of patterns using a linear combination of R-wise products. So, what we are doing is that we are considering a natural class of mappings which is obtained by the linear combination of R-wise products. Let me define what it is. And what is that? It says that you can express the mapping function as a summation like this, I mean a linear combination, but linear combination of what terms? Where the, I mean where R-wise products means R-wise products of the pattern coordinates. Okay, so we have to write that R-wise products of the pattern coordinates. Now, you see the definition of the hyperplane is that when you are describing a hyperplane equation, then the hyperplane equation will be of the form of, I mean let us say if the elements of the x vector is x1, x2, x3, x4, x5, let us say a 5-dimensional vector, then a hyperplane equation typically will be a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 plus a5 x5 is equal to 0. That will be a kind of hyperplane equation, okay, plus some constant term. That will be the hyperplane equation in the 5-dimensional space. But the thing is that here I mean it is a hyperplane, so it does not have any term like x1 square, x2 square, x3 squares, or any cross terms like x1 x2 or x1 x3 or x1 x2 x3, x1 x2 x3 x4 x5. So, all such cross terms are very much permissible. So, if we entertain all such nonlinear terms in our hypersurface equation, then we can form a generalized hypersurface equation, okay, where all such nonlinear terms and cross terms are included. Okay. If we can do that, then we are writing a very general hypersurface equation. Okay. So, this is what we are going to write. So, A I1, I2 up to IR, okay. In fact, we have to say here that xi that we are writing here, okay, I mean let me first write it down, then I will explain. So, it is of this form that there is a term, a coefficient A, which is written with a very long superscript I1, I2 up to IR, and then we have the cross terms involving this. So, which is xi1, xi2, etc., up to xir, and that summation of this is equal to 0, and it is the summation over what space? It is the summation over all this I1, I2 space, I1, I2 up to IR space. So, it is 0 less than or equal to I1 is less than or equal to I2, so on up to M0, where M0 is the input dimensionality. So, M0 is the input dimensionality, okay, and there we can and then what is xi? Xi is the ith component of input vector x. So, that means to say that in this equation that I have written, okay, this involves all the terms, okay, all the higher order terms also are included in this basic definition itself, okay, this summation. Okay, this is a very general form of representation and we call it as the rational variety of order n. So, this is called as a rational variety of order r, here it is order r, okay, because we are going up to IR. So, here it is r terms. So, we are going up to IR. So, this is called as the rational variety of order r, rational variety of rth degree we can say. Okay. Now, you see that what are these terms that we have got xi1 up to xir, that means to say that here I have shown r such terms. Now, these r terms that you are getting, that can be picked up out of the m0 total number of coefficients that you have got, or rather the original dimensionality of the input vector x is m0 dimensionality and you are choosing a number r that is less than m0. Okay. So, and you are forming an equation like this, that means to say that it is possible for you to have different combinations of this r. You have got m numbers out of which you have to pick up r numbers in different combinations. Okay. So, basically it is a combinatorial problem and all this rth order product of entries, you see this what I have written x1, xi1, xi2 up to xir, this is an rth order product. Okay. This is an rth order product. Okay. And this one is called, I mean such kind of a product term that is called as monomial. Okay. So, this x1, xi1, xi2 up to xir, the term that we have got, this product term, this rth order product term, this is called as the monomial. So, how many monomials like this are possible? We have got totally m0 number of monomials, m0 number of inputs available, out of which we have to choose r. So, that means to say that we have got m0 CR, or rather to say we have got m0 minus r factorial by m0 factorial and r factorial. These many monomials are possible. So, there are, I can say there are this many monomials. Okay. Now, out of this, okay, so what you can do is that you can have different such separating surfaces now. Okay, I mean you can, using this, since you are using all these rwise products, okay, the separating surfaces that you are going to have are not the linearly separable surfaces. In fact, you can have different type of surface separability. So, you can have, let us say that you have chosen a dichotomy of H1 and H2, right, and let us say that we have got 5 such patterns. Okay. Now, these 5 patterns, in this case, I mean in this let us say, I mean we take some examples like this. Let us say this is example number 1, this is example number 2, and let us say that this one is example number 3. Okay. Now, here you can see that this is linearly separable. this dichotomy is linearly separable. Why? Because I can find a hyperplane that separates. This dichotomy that we have got, this is certainly not linearly separable. I cannot pass a hyperplane, but possibly I can pass a hypersphere. So, this one is spherically or hyperspherically separable. Okay. And in this example, the separability is, I mean, even a hypersphere separability also is not coming in. This should be separable using a quadric function. So, this should be a quadrically separable function. Okay. Now, some very important findings that Cover had found out is that let us say that the activation patterns, I mean all this I mean different patterns that you are feeding, that is x1, x2 up to xn, these are the different patterns that you are choosing. Now, supposing that these patterns are chosen independently. So, we want that this x1, x2 up to xn, they are independently chosen patterns. Okay. And also we assume that these patterns, this all possible dichotomies of these patterns, they are equiprobable. Let me explain what I mean to say, because you should think over it. You see that there are different patterns x1, x2, x3 up to xn, okay, and they are independently chosen. And now, I mean supposing you have decided to choose n such patterns. Now, given n patterns, various kind of classifications are possible. I mean, in one of the cases there could be that one pattern is lying in H1 class, few of the patterns are scattered in the H1 class, some of the patterns are scattered in the H2 class, like this. Okay, this is possible. So, there can be a various types, there can be various types of dichotomies which are possible out of this. So, there are, let us say, a large number of dichotomies which will be possible, and out of those dichotomies, okay, I mean all are not separable, all are not separable using even this non-linearly separable functions. There are only a few which are separable. So, what Cover did was to study the probabilities that such kind of dichotomies are separable. So, what you found out was that, I mean it is based on some assumptions, that all possible, what are the assumptions? That all possible dichotomies of this, all possible dichotomies of H equal to xi, I is equal to 1 to n, they are equiprobable. So, that is what he assumed. Okay. And then he had defined a probability that p n comma m1. Okay. Why n comma n1? Because we have got n number of patterns which are mapped into an m1 dimensional space. So, if p n m1 denotes the probability, that a particular dichotomy picked at random is phi separable. Phi separable, you understand? Phi separable means that when we map into the phi space, then it gets separable. So, the probability that a particular dichotomy picked at random will become phi separable is given by Covers theorem. Proof of that is very much involved, and we are not giving that, we are directly giving the results of that. The probability in M1 is given as 1 by 2 half to the power n minus 1 summation m is equal to 0 to m1 minus 1, and this is a combination. The combination I am writing with this notation, n minus 1 combination m. Okay. So, this is the probability, and now you look at this equation. What happens when you are designing it with larger value of m1? Surely the probability increases, and if m1 is very large, then these probabilities will approach 1. Is it what we want? Yes, we want that, because the higher the probability values are, that means to say that better separability they have got. That means to say that definitely according to cover we can say that high probability is something that we are looking for. Okay, that is all for this class. Continuation in the next one. Thank you.